Paul,
Yeah.
what is the cosine of infinity? What is the cosine of infinity?
I don't know.
That's a good question.
Is it a thing?
Okay, guys, let's go over some examples here. So keep in mind, guys, that the fundamentals of limits are still there, meaning the first thing you always do if you're looking at a limit is you plug it in. Okay, L'Hopital's rule is out there, sure, but that's just one technique that happens to exist in the whole family of techniques for evaluating limits. Remember, it's only valid if you have an indeterminate form. So if you've got like a 0 over 0 or infinity over infinity, those are the two main ones that we're looking out for. Okay. And then I also threw a couple weird ones in here that like don't even really apply, and you just have to basically use some lines of reasoning that we discussed last year. So an example of that is C. What's the limit of the sine function over x as you approach infinity? Who thinks they know the answer? This is an intuitive answer. This is just one you have to just know. The answer is 0. Okay. Why is it 0? Well, let's think. Yeah. This thing just oscillates, right, between +1 and -1. So the top number of this fraction is always just some number between -1 and 1, right? But the bottom number blows up towards infinity. If you want a concrete example, it would be, well, let's say x was a million. The sine of a million divided by a million. Think about that. Well, exactly. I have no idea what this is, but I know it's some number it's something in the region between -1 and 1. And this is a huge number. So some small number divided by a huge number is going to be pretty dang close to 0. So therefore, I reason out. Now, is that a rigorous proof? No. If you guys end up taking then you guys ended up becoming like math majors, then you would take classes where you like rigorously prove that this is going to be 0. But that's engineer students. I mean, maybe as you're an engineering major, I'm guessing one of your freshman classes might cover stuff like that. Things they're called like epsilon delta proofs and stuff like that. So you basically prove that the proof would go, if you're curious, it would be for any tiny number you pick, I can always find an x value that gets us closer to 0 than that tiny number you picked. Okay, do y'all understand that?
Yes.
Okay, let's look at D. D says, what's the limit of sine squared of x over x? So, as always, you want to ask yourself, is this one, now of course, if x is approaching infinity, we know what the answer would be, right?
Yes.
0. Okay. But it's approaching 0. So you go, okay, let's plug that in. What's sine of 0 squared? 0. This is 0. Okay, great. This is a candidate for L'Hopital's rule because it's a 0 over 0 form. Indeterminate. So what you do is you say, all right, well, this is going to be equal to, let me show you, this is what I was talking about a few minutes ago. An example of a wrong answer. Like say you're taking for the AP exam. Now this is too easy of a question to be on like the free response. Like, I mean, not easy, but just there's not much to it. There's just one answer. The free response questions, as you'll see if you look at it, they have multiple parts. So I don't know, maybe they throw it in as like an afterthought. Oh, what's the limit of this function? But anyway, so you take the derivative of the top and you take the derivative of the bottom separately. Now this throws off students all the time. Why? Because they go, I gotta use the quotient rule. No, you don't. That's not what L'Hopital says. L'Hopital says the limit of f over g becomes the limit of f prime over g prime, given that it's an indeterminate form in L'Hopital's rule. So derivative of sine of x squared would be 2 times the sine of x times the cosine of x. Are we okay with that?
Yes.
That's a u squared turning into 2u prime type deal. And what's the derivative of of x is 1. That is wrong, or would be marked wrong. What am I missing? The limit notation. So that's what I was trying to point out. This is one way that people lose points on the AP exam.
That's so icky.
They would say that this equals this. No, they are not equal. This limit is equal to this limit. That is true. Oops, sorry, I wrote it as X and 7. Sorry about that. That is true. Do you guys get what I'm talking about?
Yeah.
Okay, so that's, for those of you taking the test, it is an exercise in precision, notational precision, much of it. Now, multiple choice, you can do it in your head if you want. If you've got the skill to just do that in your head, then great. So that, in my opinion, the multiple choice is really the money maker, as it were, because you're not going to get nitpicked. You're not going to lose a point on a nitpicky thing. It's either right or it's wrong. So anyway, so what's the answer then? Plug in 0. What's the sign of 0? 0. So you have 0 divided by 1. And this is when we overthink sometimes, right? We go, oh, 0 over 1. What form is that? It's not a form. All right, maybe it is. It's just a number. But 0 divided by 1 is 0. Okay. Do we understand?
Yeah.
Now, here's the thing. There's some interesting stuff happening there if you compare that to the first question. Because the first question had an answer of 1. How come it's now 0 when you squared the numerator? Well, you kind of made the numerator stronger by squaring it. And so that top now is approaching 0 faster, thus pushing the limit to 0 instead of 1. Does that make sense?
Kind of.
So again, the first one, it's the ratio between sine, and so when you guys say, oh, sine versus x, they're kind of competing with each other. And so when this limit goes to 1, it's kind of saying that these are both approaching 0 with the same pace, right? And then when you square the top, that actually makes you approach 0 faster. So now the top is approaching 0 faster than the bottom, which pushes the limit to 0.
That makes sense.
Okay. And that logic that I'm discussing there is kind of the same way you analyze a question like this, is where you just kind of thinky, winky.
Would you, if you wrote limit as x approaches 0 to sine x cosine x equals 0, would that be the point?
Yeah, this would be 100% correct. This equals 0.
Okay.
Yep. If this were a free response question, you'd probably have to show that you use L'Hopital's rule to get a point, and then you get a point for the answer. This would be a 2-pointer.
And showing that you did L'Hopital's rule,
Like if the original question was this, if this were a free response question, the first part would probably be something about like analyzing this as a function, where like you use the quotient rule and do some stuff, make some conclusions, and then later maybe like part D of the question would be, by the way, what's the limit of that function as you approach 0? And they'd be looking for, oh, it's a 2-pointer where you got to show L'Hopital's rule. That's right. Okay, should we just do a couple more? Like, you guys get the idea, or
yeah.
you feel like you're confused? Yeah, we can do as many as you guys want. And then the inverse thing's not going to take like super long to cover, but there are a chunk of questions. But I don't know. You want to look at like just down? Okay, look at E. E. So it's a 2-part process here. Really, is the first question we ask is it a candidate for L'Hopital's rule? Are we allowed? Yeah, if you plug. Yep, so the limit. Okay, so plugging in 0 gets you 1 minus 1, 0 over 0. Oh, let me show you another one. Just try to pepper these in here. How about that? Yeah, you just lost your points. Yeah, that's not a correct statement. So, derivative, so you'd say this limit is equal to, what's the derivative of this? Negative e to the x. What's the derivative of this? So the answer is -1. Make sense?
Yes.
So yeah, like if you way to check your answer on these is to like go on Desmos and graph this. And if you did that, I think you'd find a hole at when x is 0, you're approaching -1. It would be something like that. And I'm not sure exactly what the rest would look like, but does that make sense? I mean, I know it would do something like this in the long run. And just this. That'd be fun to just do it once. Just to demonstrate what I'm talking about here. You guys get what I'm talking about or no? As far as how you can check a limit with a graph?
Yeah.
Another way to check your answer is just to plug a really small number into that function. If you want to be really careful, you have to plug in a positive 0.0001 and then a negative 0.0001 to make sure they're kind of converging to the same number. But remember those ones that do this?
Yeah.
That's the Lindsay Lohan. Limit doesn't exist. Sorry. Okay, so it looks, you're like, this looks like a negative exponential growth curve, but if you go here, you can see there's a hole there. And the hole is happening at -1, so. There you go. Way to check your answer. Same thing with your, you go sine of x divided by x. You can see a lot of stuff here. One, you can see it approaching 0 for large x values, and you can also see it approaching 1 when x is approaching 0. Okay? All right. A couple more, and then we move on, or? I don't know.
Which one's the coolest?
The coolest?
Yeah. Most gamer.
Most gamer?
J.
Sure. None of them are I guess I made a note that that 3L is tricky. You look at that one.
But J.
I'm just looking for one that's like maybe particularly interesting, but they're
Why is 3L particularly tricky?
Who knows?
some of them are a bit more involved, I guess. Let me make sure we go over one where. Sorry. What was that?
When you do this, you get one step everything.
Yeah, here's an exercise. Why don't you look at these, maybe on number 2. Can you find one on number 2 where the limit doesn't exist? And I'll give you, this is probably too big of a hint, but it's one where L'Hopital's rule doesn't even apply. It's not even relevant. But I'll show you when you find it, I'll show you how it is. L'Hopital's rule can lead you to some wrong answers if you don't apply it correctly. D? Very good. D, the limit exists, but L'Hopital's rule doesn't apply. And C is one where, so remember, L'Hopital's rule says if you have a 0 over 0 or infinity over infinity form, you can apply the rule. But on 2C, so let's look at that. You take your first step and say, let's plug 1 in. You get 2 over 0. But wait a second, that's just undefined. So this is a does, this limit does not exist. It's a DNE. Okay? Yeah.
Is the one for 2J DNE or no?
2J?
Yeah.
2J, very good, because the cosine of 0 is 1. That one's a DNE. You're just right off the bat DNE. You guys hear what Alyssa said? That's a good observation. So here's the thing, though. This is where you got to really watch out, because you might go, okay, that's fine and all, but what would have happened if we had done L'Hopital's rule? We would have erroneously. This is a wrong, incorrect logic. But if we had turned this into 2x over 1, we would have thought the answer was 2. So if you apply L'Hopital's rule when it's not valid, you're going to get some wrong answers. It's going to make you think that it's. Same thing with D. What's the answer to D? 0. If you plug in 1, you get 0. Game over. No need to manipulate that. F is worth looking at, just2F, because.
Does that say x squared?
Yeah, sorry, I was supposed to say x squared minus 1.
And that's same with e.
Yeah. What's the answer to E? 1. Because if you plug in 1, you just get 2 over 2, which is 1. This one, does this ring a bell for anyone? Well, can you use L'Hopital's rule here?
Yeah.
It's 0 over 0.
You'd get, it's a 0 over 0 form. So 0 over 0 form. You'd get 2x over 1, which would get you an answer of 2. But I just wanted to throw out here, this is one we did last year. What was the only method we had for the 0 over 0 form last year?
We
had
find
back
the
under.
Yeah, we would have done this. We would have written that as x minus 1 times x plus 1, and then canceled out the x minus 1s, leaving this, and then plugged the 1 in, and we would have gotten to a different way. So there you go. L'Hopital's rule agrees with, our old methods that, I hope, obviously, it would be very upsetting if it didn't.
I would revolt.
You'd revolt, yep.
Like that time when I was trying to convert inches to feet. God, I still don't know what was happening there.
Okay. Let's go over 1 or 2 more examples, and then I'd like to spend 15 minutes covering the inverse. Let's just do one more example. I want to make sure I don't want to have to rush through the inverse. I don't know, one of these wacky. I don't know. 3. I was just looking at that one.
Because it's not the division. What do you, I would cross. I am right now.
Oh no, I was looking at I. Sorry.
Damn.
This is I. We can do both. 3I. I don't know. Just maybe this isn't that interesting. I just thought
It just looks disgusting.
it just looks a little scary when you first look at it.
No, disgusting.
I was looking at this marker with life left in the tray. Feel kind of bad throwing it away prematurely. But like these markers that don't write very dark, they still have some purpose. Anyway, is L'Hopital legit here? Can I do it?
No.
This is 3I. Let's try it. Plugging in. If you plug in 1, you get 1 minus 1 over 2 minus 2. Yep, cosine of pi is -1.
Oh, sorry, that's a minus.
That's one to look out for. Yeah, you could change this into more of a trick question by changing that. Yeah, make that a minus sign, and then L'Hopital wouldn't apply. But L'Hopital applies here. It's 0 over 0 form. So we're going to say that limit is equal to this 1. So the derivative of this top would be 1 And what's this cosine term going to turn into?
Minus.
Negative, and then don't
It's
forget
negative pi sine.
pi sine of pi x. Not like that pi is going to really matter in a few moments, but
No.
Well, it's there anyway.
it's there. Plugging in the 1, what's sine of pi? 0. So the answer is -1/2.
No.
There we go. Anyway, I hope they're not like too horrible. So the trick to the last one, the one that I said was tricky, is just to write it like this.
Hold on.
The last one, 3L.
Oh, okay.
Because you might go, well, wait a second, how are you ever going to get like because all the indeterminate forms are like infinities over infinities or zeros over zeros. And then you kind of have to do a little hand waving here to talk about,
And later.
well, you have to do this thing where you say, well, I mean, I can't really plug 0 into either of these, but based on my knowledge of how the log function behaves and how the 1/x function behaves, you know, something's going on here of these are both kind of like infinity over infinity.
Okay.
Because
Yeah.
log as if x is really close to 0, log is enormous, and so is 1/x. They're both really huge. Right?
Hold on.
No? Doesn't make sense?
Oh, yeah, that does. Okay.
So,
Now that I'm looking at it, I try to go change this. Technically, this is what I should be asking. That's my because this function doesn't even have a domain over here, so you can't really approach from the left. Remember, limits you got to approach from the left and from the right. But you can maybe argue that you can infer that there should probably be a little plus there. But you get what I'm talking about? So now the hand waving argument is to show that okay, L'Hopital could be applied here because they're both approaching infinities. Now, granted, this guy's approaching a negative infinity. This guy's approaching positive infinity, but still the same thing holds, same idea holds. So the derivative of this would be 1/x. The derivative of this would be -1/x squared. And then you manipulate it. That would turn into -x, which suggests that I should be approaching 0.
Okay.
No? Doesn't make sense? Or
I got it.
no?
no.
I see one.
Here, bring it back, Mr. Well, do you get that last thing, the last step where?
Yeah.
Well, okay. Well, do you get how this guy's derivative is this? Hopefully,
Yes.
please say yes. This guy's derivative is this.
Yeah.
And then do we all get how this simplifies to this?
Yeah.
And then do we get that? I'm using sloppy, bad notation, right? But painting myself into a corner here. But we're still talking about the limit as x approaches 0. So what's the limit of this as x approaches 0? 0. And then here's the graph. Mr. Desmos confirms. What's weird is this time Desmos has failed me. Bro, you can't plug 0 into that, but okay. We can see that. Clearly you're approaching 0 as x approaches 0. Oakley dokley, feel okay about that?
Like, why does it think he can plug 0 in?
I don't know. He's a computer.
Yeah, but computers usually know.
I can't come to doubt the great machine.
The engineers that work on Desmos are amazing. No, I mean, it would be so hard to be like, oh, make sure that your thing never makes a mistake. Like,
Yeah, I know.
But it's the great machine.
Yeah, no, Desmos is actually probably the best invention.
yeah, if you compare this to what I had for graphing, like a TI-83, it is incredible how sophisticated this is for like just a free thing that runs in Chrome. It's incredible.
It
But
is incredible.
even 10, 15 years ago, you'd have to pay hundreds of dollars for software that would be inferior to this. And now it's like, just You could have the, it runs on a Chromebook. It's wild.
It is wild.
Okay, guys. Inverse functions. I think I have just enough time to get you through the basics here. These questions are meant to kind of run us through the whole idea. So remember, the general idea behind an inverse function is, like on this first one, functions, they have a domain and a range. For number 4, if f maps 0 over to the number 5, then what does f inverse do? Maps 5 back to 0. Remember that basic idea?
No.
So f inverse of 5 is 0. Okay. How about number 5? Number 5 says if g of x is equal to f inverse of x, which is g and f are inverse functions of each other, and f of 2 is 0, then what's g of 0?
2.
Number 6 says if the graph of f contains these 3 points, what are the 3 points that are going to live on the inverse functions graph?
Is it 3, 0, 5, 2, and 7, negative 7, 6?
Very good. So if f contains the points, so it's back to this idea, 0, 3, 2, 5, and 6, negative 7, the inverse function would just swap the x and the y values.
Wow.
That's all there is to that. Okay. For number 8, it's asking us to look at this graph and draw the inverse function. So some of you guys might remember the more general result here of what happens. If not, just apply this idea to every point on the graph. So for example, that little end cap there at negative 4, 0, where's the point going to be on the inverse function?
0, negative 4.
So there's the graph. So this point now lives, I'm just doing this idea, just swapping the x and y. So negative 4, 0 becomes 0, negative 4. How about the point 0, 1?
1, 0.
1, 0. So let's connect those. And then the point 1, 3 becomes 3, 1. And that arrow looks like it's over there at 4, 5. So then 5, 4. You guys remember the moral of the story, geometrically speaking? It's a mirror reflection. So it's a reflection over the line y equals x, which I hope makes intuitive sense that swapping the x and y's corresponds to reflecting over the line where all the x's are equal to the y's. Okay. Great.
The swaps.
Yeah. I might have to cover the whole derivative thing tomorrow. I don't want to try to squeeze it in super fast here, but look at the slopes though. You can probably figure out the big idea here is actually contained right here. For example.
So they're the reciprocal.
Yeah. Look at the slope. So like this slope is 1/4, and this slope is positive 4. This slope is 2. This slope is 1/2. This slope is, was it 2/3?
Who knows? Magic.
Oh, you have a grid right in front of you. But slope is 2/3. Slope is 3/2. Does it make sense? But this is what makes the final thing a little bit more complicated though, because like the f has a slope of 1/4 at this point, but the inverse has a slope of 4 at this point. So what you have is this relationship where the slopes are reciprocals. So the derivatives are reciprocals, but at a different x value. You understand?
Yeah.
So that's what we'll be, we'll have to wrap that up tomorrow because we're out of time. And we'll finish up this is all just more review of just, here's a table of values. What's G of F inverse of something else? And it should be relatively straightforward, but then we'll get into the details of how the slopes relate.
Yeah.
Yeah, indeed.